Okay, so today I want to talk about quantum numbers and electron configuration. So this is basically what we've been waiting for, trying to figure out exactly where electrons live. So you remember from the last time when we talked about the ideas of the quantum mechanical model, we're talking about the 1920s, and we have a lot of people who are working together to figure out exactly where electrons live and how they behave. So we had Werner Heisenberg with the uncertainty principle, and if you remember, he said there that we couldn't determine the location of an electron and its speed at the same time. And we had Louis de Broglie, and what he was working on was the fact that electrons have wave particles. And we talked about that the other day, how electrons can behave like waves and how they can behave like particles. And then we have Erwin Schrödinger, and he gave us what is going to sort of become where the electrons live. So it's a mathematical equation called the wave function that uses probabilities and ends up giving us our quantum numbers. And a simplistic way of thinking of quantum numbers is sort of an address of where electrons live. So Schrödinger, he developed a fairly complicated mathematical equation that tells us the behavior of and energy of subatomic particles. And it takes into consideration both the particle and the wave behavior of electrons, and it puts it in terms of this thing called a wave function. And what the wave function is this mathematical equation whose answer is actually the probability of finding an electron. And so this leads to quantum mechanics. And what that really says is that we cannot pinpoint an electron in an atom, but we can define a region where the electrons can be at a particular time. So this, when we first drew the electron cloud, we sort of drew it as this shaded series of dots around the nucleus. And the darker the dots was sort of the idea that there would be a better chance of finding an electron. Well, that's called a probability map. And that 3D space where we are likely to find an electron is called an orbital. Okay, so trying to put quantum numbers to these things that we have learned. So first off, each electron has a set of 4 quantum numbers. And each electron in an atom has to have a completely different set of quantum numbers because, like I said before, the quantum numbers are basically the address for an electron. So no two people can have the exact same address because we're talking about the place in space where these electrons live. So it takes 4 numbers to describe the exact location of an electron. Okay, so the first quantum number is called the principal energy level. And we know because protons and electrons are oppositely charged, there's going to be some attraction between the protons that are in the nucleus and then the electrons. And because of that energy and pull that exists between them, we know that it will have to take energy for us to pull the electron away from the nucleus. So we describe the energy levels as those that are closest to the nucleus are actually our lower energy levels. And then the ones that we've had to put more energy in order to get the electron to move further from the nucleus, we call those the higher energy levels. And each one of those is described by an integer, where 1 is closest to the nucleus, or again, the lowest energy level. Okay, so this should remind you back of Bohr's model. And I know I said that Bohr's model is not completely correct, but we can still get some useful information from Bohr's model. And so what I'd like you to get from this is that you can see here that we have our proton in the middle and we have all of these energy levels. So each one of these integers is going to be the principal quantum number. So if an electron normally is found in level 1, if that electron absorbs some energy, it is able to move up then to energy level 2. Eventually that electron has to go back down, and when it does go back down, we're going to get the energy given off, or the light that we have seen. Okay, so after your principal energy level, the next are the subshells. And the subshells are really sort of the area that is defined by that wave function that's going to tell us the general area of where an electron could be found. So there are 4 types of subshells. There are S, P, D, and F. And each one requires a different amount of energy for the electron to be there. Remember, the further that an electron gets from the nucleus, it's going to need more energy. Why? Because there is an attraction between the nucleus, which is positively charged, and the electrons. So the lowest energy level subshell will be S, and the highest energy subshell is F. So when we're talking about these subshells, we describe them by their principal quantum number, or their energy level, and then the subshell type. So if you wanted to look or you wanted to describe an s orbital in the level 2, then you would say 2s. So this is kind of how these break down. So over here on the side, these n numbers, those are our principal quantum numbers. When n is 1, that's a very small area, and we can only have the s subshell. When n is equal to 2, it gets a little bigger. That means we can have subshells s and p. And in 3 here, it's a little bigger. We can have subshells S, P, and D. And then finally in 4, we can have S, P, D, and F. So they're actually subshells that go up to level 7, they're principal quantum numbers that go up to level 7, but subshells, as far as we know at this point, only go to F. But of course, if scientists continue to create more elements, maybe we'll find out that there is a subshell beyond F. Okay, so within each one of those subshell areas are going to be where the actual orbitals are. And an orbital is an area of high probability where the electron is located. Now remember, that's calculated by a complex mathematical equation given to us from Schrodinger. So each one of those S, P, and D, and F has a specific shape that goes with it. So S has just one orbital. It's the most basic form, and it holds 2 electrons. P has 3 orbitals and holds 6 electrons. D has 5 orbitals and holds 10 electrons. And F has 7 orbitals and holds 14 electrons. Okay. So that's sort of all of the background information that you need in order to jump into doing electron configuration. And you might say, okay, well, what is electron configuration? Well, electron configuration is just how the electrons are specifically arranged in an atom. We have 3 methods that we use to write electron configuration. I'm going to show you all of them. And the first one is called the box and arrows. And the second one is spectroscopic notation. And the third one is noble gas notation. So The one called spectroscopic notation, just so you know, that one is actually just what I would consider regular old electron configuration. So if I ask you to give me the electron configuration for carbon, I would expect you to report it back to me in spectroscopic notation. So before we can do some electron configuration, we have to go over the rules that um, are the basis for how we put electrons into those different orbitals. Okay, so the first rule is called the Aufbau principle. It's a German word that means to build. And what this principle says is that we will always put electrons in the lowest energy orbitals. So what's over here on this graph is a listing of the order that we fill the orbitals. And I actually have a cheat sheet that I will give you in class for this. So we can have our lowest energy shell down here is 1s, and that's where we are going to start putting all of our electrons. And then we're going to move up. After we fill 1s, we'll move to 2s. And you have to remember that I said that s holds 2 electrons. So this guy will hold 2. This guy holds 2. After that, we move to 2p and then to 3s. So if you kind of follow the level or how high these things are, you can figure out the order at which you're going to fill them. Okay, so the other rules for electron configuration. So we went over the Aufbau principle. Next is Hund's rule. Hund's rule says electrons are placed in their own orbitals before doubling up. How I like to think of this one is that nobody really wants to have a roommate. And so if possible, everyone would rather be in a single room. So electrons are just like people. They would rather be in their own separate area before they have to double up. And then, if you remember, I said back at the beginning there are actually 4 quantum numbers. And so the first quantum number was the principal quantum number. The second one is the subshell. The third one is kind of the number of electrons that are in that shell. And then we need a way to differentiate the 2 electrons that are in each orbit. And how we do that is to give them a spin number. So we say that one spins up and one spins down. And if you ever had to write this, you would actually say that the one that spins up is called plus 1/2, and then the one that spins down is negative 1/2. So it's just a way to give a sort of number to the final quantum number. Okay, so I think we have everything that we need to do in order to do some electron configuration. So we're going to start at the easiest element, and that's hydrogen. So the first thing that you want to consider when you are doing electron configuration is how many electrons does the element have? Because the number of electrons that it has are going to affect how you do the electron configuration. So the easiest one, of course, is going to be hydrogen because it has 1 electron. And so if we're trying to figure out where we're going to put that 1 electron, I want you to think about down here in the 1s area. And the reason that we put it there is because it is the lowest energy level. So how we show an electron in that orbital, the first thing I'm going to show you then is the box in arrow notation. So what you're looking at here are the boxes, and I'll show you how we put the arrows in. So hydrogen has 1 electron, and so we're going to look at placing 1 arrow in this box, and I usually start my first electron with the arrow pointing up. Right? And now I want to give the give the actual electron configuration for this, and I would write it as follows: 1s1. And this tells me that I am in the first energy level, I am in the s subshell, and I have put 1 electron in there. Now, I know I said that there were 4 quantum numbers, but when you're actually doing electron configuration, you don't have to worry about the spin notation. So when we're doing it like this with the box and arrows, we're kind of taking care of spin because we showed this one going upward. So this is kind of shows the positive spin. But when you write it out in that spectroscopic notation, you don't actually have to worry about the spin. Okay, let's move on to our next element, which is, of course, helium. And helium has 2 electrons, so we need to figure out how to place 2 electrons. So because the s subshell will hold 2 electrons, we're going to start at our lowest energy level, which is 1s, and we are going to insert 2 electrons. So let's take a look at what that looks like. All right, so this is the box and arrow notation for helium. So note that in the 1s subshell, we have 2 electrons. I have one pointing up, which is for the one that has the plus 1/2 spin, and then I have one going down that represents the one with the negative 1/2 spin. Now you might be thinking, okay, well, what is the spin thing? And spin is a little bit of, maybe a bit of a misnaming, and because I mean, maybe you're thinking like one spins clockwise, one spins counterclockwise. It doesn't matter really what you use, as long as you have something in your mind for spin to say that there is a way to differentiate between these two. Okay, and then the spectroscopic notation for helium is going to be 1s2. We're in the first energy level, the s subshell, and it has 2 electrons. Okay, and we are going to move along the periodic table to the next element, which is lithium. And lithium, of course, has 3 electrons. So since lithium has 3 electrons, we know that we're going to be able to fit the first 2 down here in the 1s, but then we have a 3rd electron. So where could we possibly put that? So let's take a look at that configuration. And with lithium, we have our 2 electrons down here in 1s, and then 1s is full. So our only other option is to move to the next energy level. So remember, 1s is the lowest. We're moving up to the next, the highest, but it's going to be the next empty low energy subshell. And we're going to put 1 electron there. So our spectroscopic notation says energy level 1, subshell S, has 2 electrons. And energy level 2, S subshell, has 1 electron. Okay, I'm going to go a little bit faster on the next one. All right, so we have beryllium. Beryllium, of course, is going to have 4 electrons. So with placing 4 electrons, we are going to have 2 in the 1s and 2 in the 2s. So we have 1 electron up, 1 down, 1 up, 1 down, and we have 1s2, first energy level, s subshell, 2 electrons, and 2s2 is the second energy level, the s subshell, and 2 electrons. Next we have boron. Boron, of course, has 5 electrons. And so when we go to place these 5 electrons, the first thing that you should be thinking is, well, I can put 2 in 1s and I can put 2 in 2s, but then what do I do? So again, we're going to be moving up in energy level. So to complete boron, we have 2 here in 1s, 2 in 2s, and then we have 1 electron up here in 2p. Our spectroscopic notation is 1s2, 2s2, 2p1. Okay, so next I'm just jumping to carbon. Carbon, of course, has 6 electrons. And so when we go to put the arrows in here, remember that we had the Pauli exclusion principle, which says that each electron wants to be in a separate room before they double up. So when we get to that 6th electron up here, because we have 2 and 1s, 2 and 2s, I put the first one here, that would have been boron, and then when I put this electron here, I had to move to the next orbital over. So I don't want to double up here and put an arrow pointing down. I want to move over and put one up. Okay, so once we go past carbon, we get to nitrogen. Nitrogen, of course, has 7 electrons, so let's take a look at that. And we have 7 electrons placed, and you'll notice that this time I put the 3rd electron over here in the other empty orbital. So in P, I have a total of 3, but 1 in each suborbital. When I write the notation for that, it's 1s2, 2s2, 2p3. When you're writing the spectroscopic notation, there's no way to really differentiate between these 3 electrons up here. The only time that you're really differentiating on how those look would be when you are drawing these box and arrows. So this is just my way of doing it, but I always draw all of the up arrows first. And then when I come back and make partners for these guys, I will draw the down arrows. But that is just my personal preference from doing this for a few years. Okay, so once we move past nitrogen, we get to oxygen. All right, oxygen is going to add 1 more electron, and so we have a total of 8. 1s is still full, 2s is still full. We previously had 1 in each of these suborbitals, and now we have another electron here. And again, to tell them apart, I pointed it down, and we get an electron configuration of 1s2, 2s2, 2p4. So an interesting thing to start pointing out here is if you look at this 2p area, you can see that oxygen has the ability to gain 2 electrons. And so if we think about what would happen if we gained some electrons here, then if oxygen were to gain 2, and if that happened, what kind of ion would you end up having for oxygen? And if you think about that, in what ion we have for oxygen, if this were to gain 2 electrons, then oxygen would be a -2 ion. And those new gained electrons would go in here. And then we would end up with oxide, which is O2, oops, sorry, that's a 2, and minus, which is the ion that we have for oxygen. So electron configuration helps us out a little bit to think about what kind of ion something could form. All right, so let's finish up this period on the periodic table, and we're going to fluorine. Fluorine is now going to have 9 electrons, and so here is what fluorine looks like. We have 2 and 1s, 2 and 2s, and then we have 2 here in this sub portion of P, 2 here, and then 1 here at the end. Our electron configuration is 1s2, 2s2, 2p5. First energy level, S subshell, 2 electrons. Second energy level, S subshell, 2 electrons. Second energy level, P subshell, 5 electrons. So again, if you look here at this last part of the subshell, you can see that there is space where fluorine could take on another electron. And we know that fluorine, in fact, does take on another electron, and fluorine becomes -1 when it makes an ion. Okay, to finish up this period on the table, we'll look at neon. Neon has 10 electrons, and so what you should notice here is that everything is full. 1s is full, 2s is full, and 2p is full. So everyone has their full complement of electrons. We write the spectroscopic notation as 1s2, 2s2, 2p6. So when you move on and do electron configuration for the next element, which is sodium, our next electrons are going to have to go into 3s. When we are done with 3s, then we move to 3p, 4s, and so on until we continue to get all the electrons placed. So when you first start out, as long as you have a little cheat sheet that helps you on the order of these, they're really not too difficult. So relating our spectroscopic notation or our electron configuration back to those quantum numbers, remember that these integers out front, so this is just looking at fluorine again, so 1, 2, and 2 represent the principal quantum numbers, those energy levels where the electrons are. The S, and P represent the sublevels or the subshells where the electrons are. And then the 2, 2, and 5 tell us how many electrons are in each one of those subshells. And so remember that it doesn't tell us like where in the P these 5 are, but we fill each one with 1 before we start doubling up. So electron configuration has a lot of rules to it, and as long as you follow those rules, you will do pretty well. But of course, everything that has a rule has exceptions to the rules. So we have to go over the exceptions to the rules, and so let's cover those. And the exceptions to the rules I will go over in depth in class, but I wanted to make sure that I touched on this just so you wouldn't be surprised. So some electron configurations don't follow the exact rules as they want. And you might say, well, why is that? You said that there are these rules and that they should follow them. Well, anytime an element ends up breaking a rule, if you have an atom doing something that is out of the ordinary, it usually is because of one reason. And that one reason is that it's energetically favorable. So whatever that electron is choosing to do, it is because it is energetically favorable. So one example would be copper. If you started adding electrons to copper, you would think that copper would end up being ending with the at 3d9, but copper ends up doing this weird thing where it promotes an electron from a lower energy level up to the D level. And I will go over that with you specifically in class and show you some of these exceptions to the rules. Okay, and before we say that this video is all set, I just wanted to show you that there is one other way to write these electron configurations, and that is a shorthand notation. So if you can imagine for a minute writing the electron configuration for a really large atom, something that has a lot of electrons, maybe something like mercury with 80 electrons or bismuth with 83, you're going to have a very long electron configuration. So one of the things that you can do is to use a noble gas configuration. You put the noble gas element symbol in square brackets, and then you put the remainder of the electron configuration. So this is just for fluorine that we just did, and using helium is not that common for shorthand notation because helium is really just standing for 1s2. And so since it's standing for 1s2, it doesn't really save that much writing. But if you are doing a much larger electron configuration, using shorthand notation can really help you. So again, we will discuss that in class, and I hope this gives you a good beginning for understanding electron configuration.